Did the universe really start with the Big Bang or something else? That's the question I want you to carry with you as we dive in today.
I'm Richard Feynman, or at least I'm going to talk to you like I am, and we're about to explore the origin of everything, the very universe itself, from a perspective that might surprise you.
You've probably heard that the Big Bang was the beginning of time and space. That's what most people think. But what if the story isn't quite so simple? What if the universe didn't start with a bang in the way you imagine, but emerged from a cosmic whisper, a quantum fluctuation so tiny that it's almost unimaginable? Stick with me, because by the end of this video, you'll see the universe and the act of questioning it in a whole new light. People love neat beginnings and make sense. The Big Bang seems tidy. A singular moment, all matter and energy compressed into a point, and then boom, the universe expands, galaxies form, stars ignite, life eventually emerges.
It's a story with a clear starting line. Classical physics, Newton's world, tells us that for every effect, there's a cause. Time marches forward in a straight line, cause and effect, action and reaction.
That's the universe according to the old rules, and it's comfortable, it's logical. Cosmologists used to take that for granted. The Big Bang looked like the ultimate cause, the first domino in the chain.
We've all seen the images, a fiery explosion, a clock starting, history unfolding from that moment. It feels final. Classical physics has limits. Oh, it works beautifully for planets, rockets, even bouncing billiard balls. But when you zoom down to the very smallest scales, down to atoms and subatomic particles, the classical picture falls apart. It can't tell you what really happens in the quantum world, where particles blink in and out of existence, and probability rules more than certainty. Classical physics would say the universe had to start with a bang.
Quantum physics asks, why not something else entirely?
And that's where curiosity comes in. You see, I've spent my life asking questions that others take for granted.
Why does this work? Why does that happen? What if we're missing something? The scientific method isn't about memorizing what's true. It's about poking, prodding, thinking in ways that sometimes seem a little reckless.
People used to think quantum mechanics was weird, even useless. I thought it was fascinating. You see, curiosity is the secret. Curiosity is what leads you to challenge assumptions, to say, wait a minute, could the Big Bang not be the absolute beginning? Now let's peek behind the curtain of quantum mechanics, the theory that changes everything. In the quantum world, particles don't behave like tiny billiard balls. They exist as probabilities. They can appear out of nothing, vanish, and reappear somewhere else entirely. Imagine a particle just popping into existence for a moment, only to disappear again.
The vacuum isn't empty. It's a seething sea of possibility. It's jittering with potential.
And if particles can spontaneously appear and vanish on the smallest scales, couldn't the universe itself emerge from something like that? Could the cosmos have flickered into existence from a kind of quantum nothing? It's a question that makes you squirm with wonder, because it's not just abstract theory, it's the frontier of understanding everything. I never really cared about accepting the official story. I wanted to understand deeply and intuitively. So when it comes to cosmic origins, I didn't just take the Big Bang as gospel. I asked, what existed before?
What does it mean for there to be nothing? And how does quantum mechanics let something arise from, well, almost nothing? It's subtle.
The Big Bang may not mark the absolute beginning of the universe. There could be a quantum vacuum, a bubbling field of probabilities where the universe is just one possible fluctuation among many. It's mind-bending. It challenges your intuition. And it's exactly why you need to pay attention. Thinking this way changes more than physics. It changes how you see the universe and your place in it. When you realize that the cosmos might emerge from something that isn't exactly something at all, it teaches you about the power of curiosity, about asking questions that everyone else assumes are impossible to ask, about looking at what's in front of you and thinking, could there be another explanation? Could reality be stranger than we ever imagined? This is what science should feel like: exciting, terrifying, exhilarating. It's not about memorizing facts. It's about learning how to think. And that's the legacy I hope to share with you on this channel. I spent my life teaching quantum mechanics, giving lectures that people still remember decades later, not because I was particularly polished, but because I cared about understanding, about communicating the excitement of discovery. I want you to see that physics isn't just equations and experiments. It's a lens for curiosity. It's a tool for exploring the unimaginable. The universe may be vast, mysterious, and sometimes incomprehensible, but the act of questioning it, of poking at its edges, is profoundly human. So here's what you'll learn in this video. We're going to explore the Big Bang, not as the unquestionable start of everything, but as a potential outcome of a quantum world humming with possibilities.
You'll discover how particles can spring into existence from nothing, how the universe might have emerged from these quantum fluctuations, and why this isn't just a theoretical curiosity. It reshapes how we think about reality itself.
You'll hear stories about me, Richard Feynman, that go beyond the textbooks. My Nobel Prize in Physics, my obsession with understanding, my peculiar methods for questioning the universe, and the lessons I've learned about thinking big and staying curious. By the end, you'll see the cosmos not just as a backdrop for life, but as an ongoing story of possibility and wonder.
You'll understand why curiosity matters, why questioning assumptions matters, and why physics can be as thrilling as any adventure story. And if you stay with me to the end, you'll leave not just with answers, but with questions that will stretch your mind further than you ever thought possible.
Welcome to Feynman Flux, the channel where curiosity meets the cosmos, where quantum mechanics isn't just theory. It's an invitation to think bigger, to wonder deeper, and to explore further. Subscribe now, because together we're about to go from nothing to everything. And trust me, you won't want to miss a single moment.
What if the Big Bang wasn't really the start of everything? Imagine a universe that didn't just explode into existence, but rather emerged from a kind of cosmic nothingness, a strange quantum possibility, bubbling quietly beneath our notice. I'm Richard Feynman, and today we're going to dive into one of the most mind-bending questions in all of physics. What, if anything, existed before the Big Bang? Stick with me, because by the end of this journey you might start thinking about the universe and the act of discovery completely differently.
People have always wanted a beginning, a clean, dramatic starting line where everything begins. Cosmology, the study of the universe, has long tried to answer that question: where did everything come from? Newtonian physics was the first major framework people trusted. It's elegant, predictable, comforting. Push something and it moves, drop something and it falls. Cause and effect, a cosmic clock ticking away. But Newtonian mechanics, as brilliant as it is, struggles with the very small, the very fast, and the very early universe. It can't describe the birth of space-time itself. It can't explain how something could arise from nothing. And yet that's exactly the problem we face when we ask about the origin of everything. I've always been fascinated by puzzles that others ignore. Even as a boy growing up in Far Rockaway, New York, I would take radios apart just to see how they worked. I didn't care about memorizing facts. I cared about understanding. I once convinced a friend to help me build a small telescope from scratch, not to observe the planets, but to test whether light really bends in the way we think. That curiosity, that stubborn drive to learn deeply and question assumptions never left me. It's what allowed me to tackle questions that most scientists wouldn't touch. The universe before the Big Bang. It's exactly the kind of question that rewards a curious mind. In quantum mechanics, the rules are different. Here, particles don't behave like tiny billiard balls. They're probabilistic. They can appear, exist for a brief moment, and vanish again. Think of it like this. Imagine a quiet, empty stage. 1 second it's empty, and the next the performer materializes, dances briefly, and disappears. No audience, no prior rehearsal, just a spontaneous act of possibility. That's the quantum vacuum, and it's teeming with fluctuations. Even in what we call nothing, there is potential for something. Tiny particles can pop in and out of existence. And if this is true on the smallest scales, why couldn't the universe itself emerge from a fluctuation like this? Why couldn't the Big Bang be just one of many possible events arising from the quantum vacuum? I remember discussing this with colleagues, scribbling equations on the chalkboard in ways that probably looked chaotic to an outsider. The important thing was not to take anything for granted. Why must the universe have a beginning? I'd ask. Why must time itself start at the Big Bang? Quantum mechanics allows for states that classical physics forbids. Probability replaces certainty. Time and space could have a more subtle origin than we imagine. The Big Bang might mark a transition, a rapid expansion, but not necessarily the absolute beginning. What came before? That's the fascinating part. It's a question that's still alive in modern physics. Even as a young man, I loved to challenge assumptions. When I was in college, I built a small experiment with a pendulum and a stopwatch, just to test whether I could predict its motion precisely. My mentor thought it was trivial. I thought it was thrilling. That same mindset carried me into particle physics, where I learned that the universe is stranger and more beautiful than it seems. Particles can behave like waves. Waves can behave like particles. And from that duality emerges a universe that can't be fully described by classical rules. Could the universe itself be a particle of a grander quantum field? Could our entire cosmos be a temporary fluctuation popping into existence from something so subtle we barely notice it? These are not just idle speculations. They're grounded in the mathematics of quantum mechanics, and they force us to rethink the Big Bang entirely. Feynman diagrams, which I developed, aren't just illustrations. They're tools to understand how particles interact, pop in and out, and influence one another. They show us a universe where the improbable is not impossible, where tiny fluctuations at the quantum level can give rise to astonishing outcomes. In a sense, the universe is a giant Feynman diagram writ large, a tapestry woven from probabilities rather than certainties. And if we apply this thinking to cosmology, it opens the door to mind-bending possibilities, pre-Big Bang states, multiple universes, and perhaps even a cosmos that has no true beginning or end, only transitions and fluctuations we are only beginning to understand. This is where my approach really matters. Question everything, learn deeply, and don't be afraid to be wrong. Many of my colleagues in physics thought that asking about the universe before the Big Bang was pointless. But to me, it's exactly the right question. It's curiosity-driven science at its purest. Every calculation, every experiment, every diagram is a way of poking the universe and asking, what are you really doing here? That's the Feynman technique, not to memorize, not to accept authority blindly, but to understand the principles, to think in terms of fundamentals, and to always remain open to surprise. Quantum fluctuations aren't just tiny curiosities. They are the building blocks of possibility. In particle physics, they can explain how a particle can appear from a vacuum, how forces can arise, and even how the early universe could emerge. Imagine the universe as a sea of potential, vibrating and shimmering. The Big Bang might be just the surface wave we notice, the visible crest of a much deeper quantum ocean. It's an idea that stretches the imagination but is rooted in real physics. The universe may not need a first cause in the classical sense. Instead, it emerges probabilistically, beautifully, and unexpectedly. And this isn't just abstract theory, it's influencing modern science. Particle physicists and cosmologists now explore string theory, inflation, and quantum simulations of the early universe, all inspired by the kinds of questions I loved asking. My work on quantum electrodynamics, my Nobel Prize, my diagrams, all of it feeds into the larger quest to understand the cosmos from the smallest particle to the largest galaxy cluster. The same curiosity that led me to play with radios and pendulums as a kid drives the equations that attempt to describe what existed before time itself. The story of the universe before the Big Bang is in many ways a story about curiosity itself. It's about taking nothing for granted, about daring to think that the universe might be stranger than you ever imagined. The Big Bang may not be the ultimate beginning. It could be just a chapter in an ongoing quantum-driven tale. And as we explore these ideas, we learn more than physics. We learn a way of thinking, a way of questioning, a way of engaging with the endlessly rewarding universe. Time had no meaning, yet the universe still emerged. Imagine that. A cosmos without a tick of a clock. No before, no after, no measured seconds. And somehow it came into being. I'm Richard Feynman, and today we're going to explore one of the most puzzling, fascinating questions in all of physics. What existed before time itself? Stick with me, because this is where quantum mechanics, curiosity, and a little bit of reckless imagination collide. Let's start simple. The Big Bang theory tells us that roughly 13.8 billion years ago, the universe exploded from a singular point of incredible density and temperature. Space expanded, matter formed, galaxies spun into being, stars ignited, planets coalesced. Life eventually appeared. It's elegant, it's dramatic, it's a story that has captivated scientists and the public alike. And here's the kicker, what about before the bang? What about that first instant, that singularity? Classical physics can't answer. Newtonian mechanics, relativity, and even the early equations of cosmology hit a wall. Before time existed, before space existed, what did it mean for anything to exist at all? I've always believed that the right questions are more important than the answers. Even as a kid, growing up in Far Rockaway, I would dismantle radios just to see how they worked. My friends thought I was obsessive. I thought I was learning. One summer, I built a little homemade telescope and spent nights watching the stars, asking, why does that shine? Why does that move like that? That curiosity drove me into physics. It's the same curiosity that let me tackle problems in quantum electrodynamics, which eventually earned me a Nobel Prize, and even took me to the Manhattan Project, where I learned the serious consequences of physics in the real world. But at the heart of it all, it was always about asking the simplest questions first, even if they seemed foolish. What is time? What is space? Could the universe appear from nothing? Quantum mechanics gives us some of the strangest, most beautiful tools for thinking about these questions. At the tiniest scales, particles behave in ways that are almost laughably unpredictable. They don't have fixed positions or velocities until we measure them. They pop into and out of existence, seemingly at random. Imagine a stage where performers materialize, dance for a moment, and vanish. The stage itself isn't empty, it's buzzing with possibilities. That's the quantum vacuum. Every possibility exists at once, every fluctuation, every particle, every potential state. Only when you observe, or when conditions conspire in a certain way, does one outcome appear. Now imagine scaling that up. Could the universe itself emerge from a quantum fluctuation? Could the Big Bang be just the first observation of a pre-existing quantum state? Here's a fact not many people know. When I worked on quantum electrodynamics, I developed Feynman diagrams to help visualize these exact processes. Particles interacting, popping in and out, exchanging energy in ways that seem almost magical. Those diagrams aren't just math. They're a window into the way the universe operates on its most fundamental level. And if particles can spontaneously appear in a vacuum, why couldn't the entire cosmos do the same? Why couldn't time itself be a consequence rather than a pre-existing condition? These are the kinds of questions that make your head spin, but also, if you follow them carefully, lead to real insights. Most people assume the Big Bang is the absolute beginning, but in the language of quantum mechanics, that's not necessarily true. Probabilities can exist before classical time. States can fluctuate. Space-time itself might be emergent rather than fundamental. The universe could have existed in a sort of pre-Big Bang quantum haze, a seething foam of potentiality, until a fluctuation large enough to spark expansion occurred. It's like a cosmic game of chance, writ large. And here's the kicker: asking what existed before the Big Bang isn't idle speculation. It's exactly the type of problem modern quantum cosmologists are still exploring, using string theory simulations and concepts that are inspired by the same principles I played with in my youth. My approach to these mysteries wasn't conventional. I never memorized answers. I sought understanding. I would take a problem, break it down to first principles, and question every assumption. People call me irreverent, even playful, but that's because science is playful at its core. Curiosity, observation, experimentation. They're more fun when you don't feel bound by tradition. You start with a simple question, something like, could the universe exist without time? Then you follow the mathematics, the probabilities, the physics, and you see where it leads. Often the answers are counterintuitive. Often they're fascinating. And often they completely rewrite what you thought you knew about reality. Think about this in the quantum universe. Every possible history exists as a probability until it manifests. Particles can interact in ways that classical physics would forbid. The vacuum is not empty, it's alive with potential. Now scale that to cosmology. The universe may not have a single deterministic history. Time may not be fundamental. The Big Bang may be just a local outcome in a grand quantum landscape. That's the kind of thinking that Feynman diagrams and my own explorations in particle physics make intuitive. It's probabilistic, it's surprising, and it's exhilarating. Even during my time at Los Alamos working on the Manhattan Project, I was reminded of the importance of questioning and playing with ideas. Serious work, yes, but guided by curiosity, by a willingness to think differently, by a hunger to understand rather than to obey authority. That same mindset applies to understanding the universe before time. You don't accept limits, you test them, you explore what seems impossible, and often that's exactly where the most interesting discoveries hide. Every insight about the pre-Big Bang universe also teaches us something about learning. The Feynman technique, explaining ideas in the simplest terms, teaching as a way to understand, questioning constantly, is not just a method for physics, it's a method for thinking about anything, including the cosmos itself. When you ask, what could have existed before time, you're training your mind to think creatively, probabilistically, to embrace uncertainty as a path to knowledge. That mindset is as powerful as any equation. So what can we really take away from all this? Feynman taught us that curiosity is more important than memorizing facts. He showed us that physics isn't just equations on a page. It's a way to explore the universe, to ask bold questions, and to never stop learning. Quantum mechanics, the Big Bang, particles popping in and out of existence, these are mysteries we can approach with wonder, just like Feynman did. If you've enjoyed this dive into the mind of Richard Feynman, don't forget to like this video, leave a comment sharing what surprised you most, and subscribe to Feynman Flux for more stories that make science exciting. And remember, the journey doesn't stop here. Click on the next video and keep exploring the strange, fascinating world of physics. Curiosity never ends, and neither should your adventure. And here's what makes it thrilling. This is not a problem with a final answer. The universe before time is a frontier. Particle physicists, cosmologists, and theorists are still exploring, using quantum simulations, string theory models, and the mathematics of probabilities. They're building on the same foundations that I helped lay with Feynman diagrams and quantum electrodynamics. My work may have earned a Nobel Prize, but the real legacy is showing that curiosity, careful observation, and a willingness to think differently can open doors to questions nobody even dared to ask. So as we explore these ideas today, remember, particles pop in and out of existence. Time may not be fundamental, and the Big Bang might not be the start of everything. The universe is stranger than we can imagine, and the only way to approach it is with curiosity, playfulness, and a hunger to understand. Start with simple questions. Follow the probabilities. Let the math, the physics, and your imagination guide you. And if you do it right, you might just glimpse the universe as it was before time itself began.